Okay, so we've got an example problem on Newton's laws here. This is the one I talked about a little bit in class. We'll finish it up as promised. The thing I like about it is you've got a little bit of gravity, you've got pulleys. The only thing this problem doesn't have is an inclined plane, but that's pretty easy to modify if we wanted to. So the key here is we make a free body diagram for each object that we're interested in. And so here we have two objects, M1 and M2. Let's make free body diagrams. For M1, there is tension upward, and I'll call this T1 since I have different ropes, right? Rope 1 and rope 2, I'll call that T1. And then the force downward here is its weight, M1G. Okay, so much for that. Now for M2, well, M2 also feels a force downward, M2G. There's a normal force upward that'll take care of that weight force for us. There's no friction here. We'll deal with friction later. And then there is a force of tension, T2, that pulls it to the right. Okay, now there is one other thing in this problem that is going to move, and that's this guy, P2. P2 is a movable pulley, and the other reason we might want to make a free body diagram for it is if you think about it, you've got one tension here, T2. You've got another tension here, T1. Those two don't actually touch each other. They don't tug on each other. P2 acts as an intermediary. The pulley is actually what connects them. And so in order to understand how those interact with each other, we have to include the pulley. The pulley gets pulled to the right by the first rope, T1. And then the second rope, look, it's being pulled by two of them. So it's actually 2 T2 to the left. Okay? Now, all that's left to do is write equations of motion, so Newton's laws for each of these free body diagrams. So that's to say for M1, we can write sum of the forces in the y, that's the only direction available, is plus T1 because it points up, minus M1G because it points down, and that equals M1A1. For M2, okay, I've got two dimensions going on here. The up-down direction isn't really going to matter that much, but we'll write it anyway just to write it. Sum of the forces in the y equals plus N minus M2G, and that equals M2AY. Now, AY is 0. This block isn't moving up and down, so this is 0. So all we're really going to get from this is normal equals M2G, which is nice to know. It's not going to help us solve the problem. When we deal with friction, you will 100% need to do this step. For now, I'm just doing it for completeness. Sum of the forces in the x direction, that's the more interesting one. There's only one thing pulling on it, and that's T2. And this is going to be equal to M2A2. Okay. Finally, for the pulley, this guy's the pulley, right? So for the pulley, I've got 2. So for the pulley, 2T2 with a minus sign plus T1 equals the mass of the pulley times the acceleration of the pulley. But the problem says the masses of the pulleys are negligible. That means this is 0. And immediately, this is a really neat trick, we conclude that T1 is twice T2. Immediately, we've already started to eliminate some variables, okay? Whenever you get an equality, this is a pretty powerful thing. Okay, so we, believe it or not, are almost completely done with physics here. There's just one other physics thing that we need to talk about, and then it's just algebra. At that point, I'll pause and I'll just show you the screen. So the thing we need to consider is normally when we have a fixed pulley problem, so sometimes that's called a simple pulley, we say that if we have two blocks, M1 and M2, that if M2 moves a distance delta x down, M1 has to move a distance delta x up. They're attached to the same string, they have to move the same distance, and normally we conclude that the magnitude of A1 equals the magnitude of A2. Remember, I say the magnitudes because one's moving up, one's moving down. This case, not so simple, right? This pulley has a different string than the other pulley. They don't have to move at the same rates. In fact, they definitely won't move at the same rates. In fact, if I move M2 forward a distance delta x, then what happens is I've got delta x worth of slack now. The pulley will take half of it, delta x over 2, and the other delta x will turn into rope on the other side. So that means that this block only moves half as much as this block does. What that means is that the acceleration of block 1 the magnitude of it, is half the acceleration of block 2. And if I had multiple pulleys and multiple ropes, I'd have to figure out a similar scheme, right? But the idea is that because one of the pulleys can move, and because if I move M2, the slack that I create gets split between the pulley moving forward and increasing the length of the other side of the rope, well then, my final equation that I have left to say is that A1 equals negative 1/2 A2. So why negative? Well, one of them, M2 is moving to the right, which I defined as positive, and A1 is moving downward, which I defined as negative. So I'm going to take this substitution, I'm going to rework all of these, and I'm just going to show you the result. Okay, so algebra. You can take a minute to kind of look through what I did. If you have questions about it, of course, feel free to use the homework discussion board. It's a kind of complicated problem, but the point I wanted to make by doing it is that the procedure, even for this complicated problem, is free body diagram, Newton's laws, Newton's second law. Not so much breaking into components for this problem, but I still wrote in every direction I could. I wrote an equation in the x and an equation in the y. Apart from the unpleasantness of some of the algebra, and the tricky part of this problem, I think, is figuring out this little bit. Probably not something you'd figure out on a first shot, but now that you've seen it done, you'll have an idea about how to go about it in the future. Okay.